All right, the topic for this lesson is Gibbs free energy and K. We're looking at the relationship between the two. Now, to refresh your memory, K is an equilibrium expression. So that means that we have two reactions going at once, one forward, one reverse. And we find the value K as being the concentration of the products over the concentration of reactants. Now this is true for concentrations of solutions. Now if you're dealing with pressures of gases, K can then become described as pressure of the products over the pressure of the reactants. And then if you have a mixture of the two, which is very possible, you have some combination of concentrations in products or of pressure of products on top and concentration and pressure of reactants on the bottom of the denominator. And that value is always going to be the same, hence the word constant. All right? Now, so if we were to take a look at a particular equation, I see the smartboard's got a mind of its own today. Let's take a look at the reaction of calcium carbonate solid, and then look at the equilibrium expression for how it breaks down into calcium oxide and carbon dioxide gas. So if I wanted to write a K expression for this, an equilibrium expression, I would have K is equal to, now, we look at this and we must recognize that in equilibrium expressions, we talked about this before, that you can only deal with gases in aqueous solutions. So concentrations for the aqueous solutions and pressures for the gas portion of the program. Here we have a solid and a solid. So if we were looking at this in terms of products over reactants, then what we would have is a solid that we can't represent. So we use the number 1 because it has no effect upon the overall K value, and there's nothing that is going to change it. So we use the number 1 in multiplication to show no change. We have 1 here for the calcium oxide. I'll put a 1 above here. And then the carbon dioxide, since this is a gas, we're going to express this in terms of pressure. So times the pressure of CO2 gas. So I'll put the pressure of CO2 here. And then in the denominator, which is your reactants, we have a solid also. And that, again, is going to give us the value 1 for that. So when the smoke clears, we put everything together, multiply it out, divide it out. We simply say, in this particular case, that the K value is equal to the pressure of carbon dioxide. Okay, so when you have a mixture, you've got to be looking at the fact that liquids and solids cannot be included in that, so we use a 1 for that. And then the aqueous is expressed as a concentration. Remember, that's in moles per liter, but we don't write that in the expression. We just know that that's what it is. And then the pressure is expressed, or the gas is expressed as a pressure. Okay, another example. We have here the equation H positive aqueous plus bicarbonate ion, HCl3 negative aqueous, and this is going to give us H2O liquid and carbon dioxide gas. And we want to express this in terms of K as well. Again, we are not going to be dealing with this, so because of the fact that this is a liquid, this is not going to be included, although it is technically as a 1, but in the overall scheme of things it is not. But we have aqueous here, so these two are going to be expressed in terms of concentration, and carbon dioxide again is gas like we had in the previous situation, and that will be expressed as a pressure. So when we do the K expression for this is going to be, again, water is not going to be included, so it's the pressure of CO2 gas over the concentration of hydrogen ions times the concentration of the bicarbonate ions. And that's all there is to that. So you have to be familiar with that because that's going to come into play when we deal with the expression and the values based upon our equilibrium mixture of gases, liquids, solids. Okay? Now, in your book, you have a bunch of values for free energy, delta G at standard conditions. Is on page 817 in the chapter that we're dealing with here, and in the appendix at the very end of the book. It's on pages A9 through A15. And just to caution you that it's not done alphabetically back there, it is done as whatever group. So you need your periodic chart if you're not familiar with where certain elements or compounds can be found on the periodic chart. Okay? Now, when we look at the standard conditions for delta G, the standard conditions are identified in three aspects. It's identified in terms of pressure. So it's 1 atmosphere of pressure. In terms of temperature, this is 273 K, or of course 0 degrees Celsius, which no lab has ever run in, but for some reason that's our standard. I would think 25 degrees Celsius might be a better one, but just call me silly. And then if you're dealing with the concentration, then technically 1 mole per liter is a standard concentration, which is a lot more likely to happen, but again, not all that common, but more common than working in a lab at 0 degrees Celsius. Okay, so if it's not at those conditions, what we call non-standard conditions, then we use the symbol delta G instead of delta G 0. All right? Now, it turns out that delta G can be the value that we get in the lab, and then we can calculate the standard version, in which case if you're a scientist trying to determine if you have a valid situation, you would be able to look at or calculate the delta G standard by a correction factor. Okay, the correction factor that would bring it over to that is RT natural log of K. Now, we use K because K is for non-equilibrium conditions or non-standard conditions, either way, however you want to consider it. They're not the same thing, but they're both situations that we do deal with in the lab. Now, we talked about K a long time ago, and K is basically the same as Q. It's just not necessarily going to be at equilibrium. And that's the case here. We don't know, so we would have to go through our calculations using the K that we had put together in our two examples previous to this.